Hi everyone. Okay, so I'm going to start part 4 now. This is all still paper 1 stuff. I'll tell you when it's triple and combined. You might have to fast forward through a little bit or just listen in if you can't remember these bits. What I'm going to do today is I'm going to finish off the atomic structure, the radioactivity topic, and then I'm going to do some of the practicals for paper 1 as well. Hopefully get through that as well in the time. I'm also going to touch in on the physics and maths tutor predicted papers. You may have seen them already on the website. You can download the predicted papers. I'm going to get those up as well. Might be worth having a look at those, guys. I'm happy to post them, but you can get them off the physics and maths tutor website as well. Just so you know, the biology paper, they did meet the predictions that were made on the PMT paper about which practicals, etc., were actually correct in that paper. So it could be the case that the correction is, but remember, you've got to look at all of them. You've got 5 practicals for paper 1 if you are triple, and you've got 4 if you are combined. Okay. All right, let's get into it. In fact, I don't want a new whiteboard, do I? I want to go to the old whiteboard. Just a second. Let's try again. I think it's probably this one. When was it? 5th of the 8th. 8th of the 5th. Yeah, it's probably that one. Want to start today? Okay, why is it so small? Just let it load. Okay. If we get to the bottom of here, there's actually some things which I wrote down last time, isn't there, that I need to just remind myself to go through. Okay, so it was health and safety, and we were looking at excitation, de-excitation as well. All right, here we go. There's a couple of things with health and safety which you have to think about, because if you were a teacher, it's very different to if you were a radiation worker. Don't know why it's not working properly. There we go. So a teacher and a radiation worker. If I was a teacher, I might wear some gloves to keep myself protected from radiation. I might keep my distance. Okay, and how might I do that? Okay, well, I might use some really long tongs. So like tweezers, you know, to sort of, so I can move the radiation around, but still keep my distance. And I would reduce my exposure time. So I'm not going to tuck it into my pocket and walk around, because then I'm around it all day. You've got to limit your exposure time as well. I would also probably wash my hands, so I'll add that to the bottom here. So wash hands at the bottom, just in case of contamination, but highly unlikely in a classroom setting. If I was a radiation worker and I worked in a hospital, for example, or I worked in a power plant or something, then I may wear something a little more heavy duty. So, for example, like a lead-lined apron. Or I might have a badge. Why is that not caught up? Lead-lined apron. What's going on here? Sorry, this is going a little bit slowly today for some reason. A lead-lined apron. Okay, or I might have a radiation badge. And the radiation badge changes colour if I've been around too much radiation over time. So it sort of keeps an eye on your dose of how much radiation you've come into contact with. If you're going into somewhere dangerous, then you might even wear like a full hazmat suit. So yeah, don't sort of suggest that a teacher would walk into a room in a hazmat suit though, because that's not appropriate. Okay, so that's just a little bit of health and safety to think about there. I just want to go back and have a look at, in fact, I'll come back to excitation in just a moment. I want to actually talk about the power plant now. So I want to talk about a nuclear power plant in particular. So in a nuclear power plant, excuse the drawing here, right? But you're going to have a huge nuclear reactor. And inside that nuclear reactor, you're going to have fuel rods. Okay, and that fuel rod is probably made of enriched uranium, sometimes plutonium. And in there as well, we've got these things that come down and they're called control rods inside there as well. So we've got control rods. Okay, these control rods are made of boron. And then inside of here, we have like this liquid and it's called the moderator. And the moderator is made of graphite. Now, then obviously this all heats up because we have our fission reactions happening here. This all heats up and there's water pipes that run through this as well. But out come the water pipes, okay, from here, and it turns into like you'd expect in a normal power plant as well. With the water ends up turning to steam. Okay, and then that turns a turbine. Okay, and then the turbine is connected to a coil of wire which spins inside of a huge magnet. Okay, and then you end up creating your electrical energy. We won't go any further than that for now, but I just want you to see that it's exactly the same as a coal-powered power station. When you get from this point onwards, it just creates electricity like that because of the energy transfers. But just talking about the nuclear reactor, so this is called the reactor, okay, or the core, okay, reactor core, let's call it, okay. And inside here, we've got to control this reaction because if you remember what we said about fission reactions, so remember fission is happening in here. And what do we remember about fission reactions? It's a neutron being absorbed by a larger nuclei that's splitting into two daughter nuclei and then 3 neutrons. And of course, there's an awful lot of gamma that gets given out here as well and energy. So this neutron is key, isn't it? So here in this moderator, there's neutrons in this in the core, but what the moderator does is it slows the neutrons down. But what that actually does is it means that the uranium is more likely to absorb the neutron when it's traveling slowly. So in fact, what that does is it speeds up the reaction. All right, so sometimes we might want it to speed up, sometimes we might want it to slow down. Either way, it needs controlling because what we have on our hands here is technically an atomic bomb. And from this point onwards, remember, guys, that these 3 neutrons then go on to 3 more uranium. And what we've started here is a chain reaction. And you need at least 2 neutrons to create a chain reaction, but it's mainly 3 that comes out. So yeah, we can slow these neutrons down to make more collisions happen. I say collisions, you don't say collisions, say absorptions, okay? And then the control rods up here, what we can do is we put these down, up and down, they move up and down. And what they do is they absorb neutrons. I'll just write a little neutron like that, away from the core. And what that is going to do, guys, is that's going to slow the reaction down. Okay, so that's slowing the reaction. Of course, because we're removing these neutrons from the situation, so they can't go on to be absorbed by uranium. So you're slowing the whole thing down. Now, the only other thing I want to talk about here is the coolant, because this whole thing has a water system running through it. And the coolant will take all the heat from the core to the heat exchanger. and I'm not going to draw this. You can see it on a diagram. I can't draw a heat exchanger in detail. But yeah, the water system, often a power plant will be by the water, won't it? So that it can pump in the water and keep the whole thing cooling and not overheating. Because if it overheats, then we're talking about nuclear meltdown there, aren't we? Okay, so that's really important though, that bit about it taking heat from the core to the heat exchanger. Okay, because often it'll just, you might say, remove the heat, but we've got to be more specific, as we know, we've got to say things like that. Okay, and I wanted to also touch on, guys, talking about excitation, de-excitation. If I have an atom and it's got some electrons in its energy levels, okay, the question might say, how might an electron change its energy level? Or how might, yeah, probably along those lines is how it would be asked. So what's going to happen if that excitation happens? An electromagnetic wave comes in, it excites the electron, it jumps up in energy level and then jumps down again back to where it came from. But when it just does jump down, it gives out another EM wave, which could be of a different frequency, but that's how it happens. So remember, that's excitation and de-excitation. So excitation is when it comes in and jumps up, and then when it jumps down, that's de-excitation. But you must say EM wave goes in, EM wave comes out. Okay, so that is the whole of the topic, I believe. Is there anything else? So I've written this all on my board. So is there anything else I wanted to say? No, I think we're good to go. Okay, all right, good to go. Right, I'm gonna look very briefly now, guys, at the PMT paper. I've got a few of them up here. Oh, sorry, just to say as well, just as a reminder, the nuclear power plant and the fission and fusion bit are not in the combined paper. Okay, just to make it clear. Right, now this, I've got papers for both. I've got papers for, let's just look at the paper one. So paper one, this is what we got here. Combined science paper. Okay, so on the combined science paper, they predict that it was density that was going to come up. And then in the paper two, it was the ripple tank and the F equals MA practical. So we could take it for its word, but we're not going to ignore the other three practicals for combined science. So make sure you know all your practicals. I'm going to give you a bit of an overview on practicals in just a minute. But yeah, I will post this and I think you should have a look. This one concerns me slightly. I was looking at 2.2. The graph below shows the current potential different IV graph for a diode. Now, a diode, in this direction of the graph, in this half of the graph, it's traveling in one direction, the current. And then when you get to this point, it's changed the direction. So I just want to show you the mark scheme on this, combined science people, and just have a look. But this is for everyone, really. This could come up in anything. Explain the shape of the graph. Now, I've not seen a question like this before, and how the current through the diode depends on the potential difference across it. So let's have a look at the mark scheme. Which one is it now? Yeah, here we go. So explain the shape. High resistance in the reverse direction. So here we're talking about the resistance because look, this is a current voltage graph. So the gradient on this line is the resistance. In fact, this time it's V over. So actually it's 1 over the resistance, but you can tell something about the resistance from the gradient on this graph. So really, when you're talking about IV graphs, you really should be talking about resistance as well. So it's got high resistance in the reverse. So when it's reversed, it's here. But then look, when it goes the other direction, when the current flow changes, there's less resistance. But it says high resistance in reverse with very low or no current flowing. Okay, and then look, once the potential difference exceeds the threshold voltage, the diode starts to conduct current rapidly. Remember, on a diode, the reason why it doesn't just shoot up straight away from the cross point here in the middle is because it has to overcome the resistance in the circuit. So the current's trying to get through here and then it slowly starts to come through. But we call that the threshold voltage, and it's normally 0.6 volts. Okay, 0.6 volts is the point at which all the current will then start to flow through. So look at diodes, make sure you're happy with those, all the components in the IV graphs. So you've got a fixed resistor, and a lamp as well to know there. This is something that I brought up in my revision video, where you've got two resistors, and this thermistor here is the one that's going to be controlled by temperature. And so the potential difference across this might change. And then therefore this one will change. So if the potential difference on this one goes up, the potential difference on this one will go down. And the current in series will always stay the same. What else have we got on here? Yeah, all sorts of stuff, but have a look, please, at that example paper, which I'll post for you as well. Right, let's have a look at the triple paper for a minute. Now, on the triple paper, they have predicted in the paper 1 that it's going to be the IV graphs practical. Okay. So yeah, we've got stuff about transformers there. We've got what else have we got? Got radioactive decay. Oh, this one's a good one as well. About density. A student is investigating the properties of a cylinder of aluminium with a radius. So you've got to find the radius here. Then we've got the density of aluminium. So we know the density of that and the volume we have to calculate using this. Sorry, guys, I'm dying. Okay. The problem with this diagram here, guys, is that it's in centimeters. And so you will have to put that into meters, because you can see here your mass is actually in kilograms. Let me just get a tissue, just a second. I hope you guys don't get this before your exam. It's like the never-ending illness. I've just been ill for like ages. Right. So yeah, then it wants to calculate the mass. So you basically got to use your density equation there. What else have we got on this paper? Was there something at the end? Let me just have a quick look. There was something that worried me. Oh, here we go. Look at this question. When a gas is expanded rapidly, its temperature decreases. When we think of a gas getting hot, it expands and it gets less dense and it rises. But here, I want you to think of a scenario where you've expanded it rapidly. There's no change in temperature. You haven't put the temperature change in, but then it wants to know what's going to happen. So it's saying here the temperature decreases. So explain why expanding gas in this way causes a decrease in temperature. So if we go to the mark scheme and have a quick look, when a gas expands rapidly, the particles do work. So whatever kinetic energy they had, when they expand quickly, if you force them to do that, they're going to do work. A lot of these questions about energy transfers are always related to work done. So here, it does work on the surroundings to move apart. This work requires energy, which is taken from the kinetic energy and gas particles, leading to a decrease in temperature. So if it says it decreases, you've got to think along these lines. Then you've got to be like, right, okay, why would that happen? Well, it's got to have lost some energy somewhere. Okay, well, there must have been some work done. Okay, I'll post these papers. You have a good look through them. It might be an idea to print it off and have a go. But yeah, there's one predicted paper for you anyway. Right, let's get back to it. Let's do practicals now. Okay, there are 5 practicals for triple and 4 practicals for combined. So pracs, here we go. I have a really good document for you as well here, which I will also post. Let me give you a quick view. It is the required practicals. So we start off with specific heat capacity. Here's the diagram. And you can see here we've got a block that's been insulated because we want to keep all the energy in there. It's a circuit that's attached to our heater, and all the energy that we're putting in, we want to go into the metal block, because we're looking to find the specific heat capacity of the metal block, aren't we? Okay. So look, a heat-proof mat and everything, we're trying to insulate it to keep that energy in, because when this thermometer reads a temperature, I want it to correspond with the amount of energy that's gone in. So yeah, remember, a diagram is so helpful. We've got a little circuit here set up, etc., etc. The method, I will post this, have a quick read up of the method. But really, I just want to have a look at some of the sources of error in this one, for example. So some thermal energy is transferred to the surroundings. That is the main source of error in this investigation. The biggest problem that would be that not all the energy that you've created has gone into that block, and maybe you've lost some to the surroundings. So whatever you actually calculate as your specific heat capacity won't be right. But you need to make out as well that if you're losing energy, let's have a look at our specific heat capacity equation. So this is practical number 1, specific heat capacity. Specific heat capacity equals the change in energy over the mass times by the change in temperature. Okay, and that's in degrees Celsius. Now, if the energy goes in, if I think it's, I don't know, let's say we read it as 100 joules, the amount of energy that goes in. And remember, how do we calculate that? It's the power times time, isn't it? It's the amount of power. And remember, the power is the current times by the voltage. So I can work this out, can't I, using my ammeter and my voltmeter. I work out the power and then I times it by the amount of time that's on there. And then that's my energy. So anyway, 100 joules goes in, and I say it's 100 joules because that's what the ammeter and voltmeter said. But actually, in reality, it's going to be more like 90 if we've lost some, for example. Well, that means that our reading of specific heat capacity is actually going to end up too high. Because actually, in reality, it's more like 90. So you've got to be specific in that way, and you've got to maybe make it clear that, is it going to be too high or is it going to be too low? Look at the equation. The equation will help you every time. Okay, let's go back to our PowerPoint. Remember, I will post this for you so you can have a look through. We always need a risk assessment, etc. What else does it say here? We try to reduce this error by adding insulation, ensuring the thermometer is in contact with the block. If this thermometer is not in contact with the block properly, then it's not going to transfer the heat to the thermometer very well. So how we do that, we put a little bit of oil in there to lubricate it so that it will actually transfer the heat, because oil is a good thermal conductor. Remember that word, thermal conduction. It's how you should be saying it. Okay, all right. So I'm not going to go through the practicals all individually. I'm going to post this and you can have a look. Next to it, there is also some example questions and then a mark scheme to go with them as well. So this version I have right now is a combined one. So there's only one missing off the triple one. But I just want you to have a look through each of them. Right, the next one, we've got resistance of a wire. In fact, what I'll do is I will list them first of all on here. So number 1 is your specific heat capacity practical. Number 2 is your, now this is actually a triple one, but it's thermal insulators. So I'll do that one last so that I'm not going on too much for the combined people. And then the third one, I really want to focus in on this third one, guys, because there's actually a slight variation that they could give you. It's resistance of a wire. But it could be resistors in series and parallel. Okay, so I will talk through that in a minute and just tell you what the variation that could be on that one. And then number 4, we've got the IV characteristics practical. IV prac. And then the last one, which is very common, comes up quite a lot, is the density one. Okay, now most of the time in these practicals, you're trying to answer a question, aren't you? The question in this one is, for example, what is the specific heat capacity of the block? Okay. In this one, the thermally insulated one, which is the triple one, it's which is the best insulator. Okay, resistance of a wire. Okay, does the length affect, or excuse me, let's reword that. How does the length of the wire affect resistance, for example? Okay, so it's always a question. Okay, and then the IV characteristics. How do current and voltage vary in each component? So you're looking at 3 different components, aren't you? Okay, and then the density one, what is the density? You need to find the density of whatever object it is that you're looking at. Okay, so we're answering a question each time, aren't we? Right, every time you do a practical, I want you to follow this checklist every time. These are the things that you have to include in your practical. So I went on training, AQA training, not so long ago, and it said that it really, really, really wants you to do a diagram. If there is no diagram, draw a diagram, okay? Because you might get marks from that diagram instead of what you've written. So, in fact, what I want you to do is I want you to start with your variables, okay? And when I say variables, if you state the variables, they know that you understand the practical, what it's about, because you know the independent variable, that's what you're changing each time. Your dependent variable, that's what you're measuring. Okay, and then your controls. Don't go mad on your controls. Don't spend too much time on them, because often that's not actually in the mark scheme, but it gives you an idea though what you might talk about in terms of error at the end. So it is something good to sort of get in there. Keep the same. All right, so we mentioned our variables. Remember as well, in a practical, you should be writing in full sentences, really. If you write in bullet points, that's fine, because you can see it clearly down your page, but you must write in full sentences, please, okay? So variables, and then we're going to do a diagram, and we're going to label that diagram, okay? This blooming thing. Right, so then we're going to do a diagram. Then we're going to do make sure that we've mentioned every piece of equipment. And I don't mean list your equipment. For example, I will measure the current using a ammeter. You've got to say the piece of equipment. But you know what people always miss off? I will measure the length of the wire. Using a ruler. Yes, state the obvious. You've got to give me the pieces of equipment. So mention all. Okay, I want all of the equipment mentioned at least once. Do not say these words. Amount. That's banned. It's too vague. You're going to say the volume, for example. That's like very specific. Don't say scales. That is also banned. You're going to say top pan balance or balance scales, but you can't just say scales on their own. Then I want a range that you're going to test over. For example, if it was the resistance of a wire one, I'm going to go from 10 centimeters to 100 centimeters. Just let it catch up. Okay, then I want intervals. What I mean by that is maybe every 10 centimeters. This is the bit that people always miss off, is the range and the intervals. Change the way in which you are writing about things now, guys, because some of you start writing a paragraph and you're just waffling on about things. These are the things you need to hit, okay? And be really concise about it as well. So what else have we got? So we've got equipment, range, intervals. Next, you need to think about, is there an equation which I'm going to use? For example, if it is resistance of a wire, it'll be resistance equals V divided by I. I'll need the voltage and current readings, for example. What else will I need? Sorry, if it was the IV one, I'd need resistance equals V divided by I. Do I need to do a graph? Not in every one. I might not. In fact, the density practical, you're not needing a graph, are you? You don't need You don't need that. You don't need a lot of this in the density one either, but at least you've been through the checklist and made sure, because this is the case in most cases. Equation, then we've got the graph. Right, repeats. Oh, I should have put this in before, shouldn't I? Repeats are up here, but I'll write it down here. Repeats. Right, there's a sentence that comes with repeats. Do not just say, I will do 3 repeats. You must say, I'm going to do 3 repeats. Okay, I'm going to calculate a mean. Then I'm going to say, I'm going to remove anomalies. Then I'm going to say all of this to reduce the effects of random errors. So that's the sentence that goes with repeats, and you're going to apply that wherever you can, okay? Don't just say I'm going to do 3 repeats and then leave it at that. You've got to be more detailed. So we've got repeats, then we've got a graph, we've got equation. What else have we got? Health and safety. So you might talk to me about a risk or a hazard. Okay. And then how are you going to prevent? What are you going to do to prevent the risk? Okay. I think I've got everything on there now. Remember, not every single one of these applies to every practical, but it really gets you thinking about, have I included everything? The density one is a little bit unusual in that sense because you're describing just the method. There's not really intervals, there's not a range. You still might do repeats though. There is an equation, you don't have to do a graph. So guys, you need to watch the videos again on your practicals and make sure that you know them. But please follow that. I'll post all the resources I have up for you. Watch all the videos on free science lessons or Malmesbury Science. They're really good, aren't they? If you just type into Google, required practicals, AQA, physics, right? They'll all come up, and just watch the videos on them. So the last thing I want to go through, guys, is I want to go through this practical here with you. So you can look at all those practicals individually. Look at the sources of error. That's what I didn't include. Let me go back to this. What's the sources of error? That shows the examiner that you really do understand what this was all about. So what's the error and how to avoid? So for example, on this specific heat capacity one, the source of error would be that energy would be dissipated to the surroundings. What am I going to do? I'm going to insulate that. Okay. So be thorough. Practice those practical questions. Go back to the PowerPoint here. Okay, so I want to just talk you through this one now. Remember, resistance of a wire is, in fact, I just want to check the spec. Just bear with for a second. Right, I'm just looking through the resistors bit on combined science, everyone. Right, okay. For combined, you don't need to know resistors in parallel, you just need to know resistors in series. So if I put resistors in series, I just add them up, don't I? So it's highly unlikely this part of the practical would come up in the combined science one, but I'll go through it nonetheless. So the usual one is if I increase the length of wire, what's going to happen? But then it could move on to, well, if I wanted to check resistors in series and then resistors in parallel, how would I investigate that? So on my whiteboard, let me just show you quickly. So let's have a look at resistors for a moment. So remember, if I put resistors in series like this, and this is combined, come on, computer. Not happy. Come on. There we go. Okay, so these are resistors in series. Imagine this is 10 ohms and this is 10 ohms. Okay, the total would be 20 ohms, wouldn't it? Okay. And then if I put them in parallel, okay, 10 and 10, then how I would work that out, guys, is it would be, so here I just do resistor 1 plus resistor 2, but here I've got to do 1 over resistance total equals 1 over resistor 1 plus 1 over resistor 2. Okay. So if I wanted to investigate this, I need to just look at creating well, I just need to see what the resistance is. So how do I calculate resistance? Resistance equals voltage divided by current. So if I'm going to investigate this, I need to know what the current is traveling through each of these, but I also need to know what the voltage is over both of them as well. So what would the voltage be over here? And then what would the voltage be over here? So you just need to know where to put your voltmeters. So you put them in parallel with the setup. So here I could work out the voltage over the two in series, and then here I put them in parallel, and then I get the voltage over them parallel, and then divide it by the current in both cases. And what we will find in that investigation, guys, is if it's 20 ohms here, it's going to be a lot less here, because it's going to be 1 over resistance total equals 1 over 10 plus 1 over 10. Okay, so we've got 0.1 plus 0.1. So 1 over resistance total equals 0.2. And then resistance total is going to be equal to 1 over 0.2. Yeah, and then we're going to end up with a resistance a lot lower than what our 20 ohms was to begin with. Okay, so 5 is a lot lower than what 20 is. All right, guys, so it's quite easy when you think about it. How would I practically find that out? Well, I've just got to find current and voltage, and I've got to put my voltmeter like this over the top of the two resistors in series, and then like this over the top of the two in parallel. Okay, so again, I will post those practical things on this PowerPoint. Have a look through them. There's some good example questions and mark schemes to go after them. So what else have we got? And then we've got our IB characteristics one. This is the one that the physics and maths tutor is predicting will be on there. Please remind yourself that this setup here, you see how you've got your circuit? This is a variable resistor. We put the variable resistor in this circuit so that we can vary the current. Okay, we need to measure the we need to change the voltage and measure the current. But if we don't, if we leave this circuit on, it will overheat and the current will get too high, okay? So in order to control that current, you can use your variable resistor to vary that current in the circuit, okay? And keep it at a measurable value. So here it says here, oh no, it doesn't say that, does it? Let's have a look. Here we go. Switch on the circuit, record the ammeter and voltmeter readings, switch off the circuit to avoid overheating. The ammeter used to measure the current, the voltmeter used to measure the potential difference. The resistance of the component is calculated using resistance equals V divided by I. The resistance in the variable resistor is altered to change current in the circuit, and steps 2 to 5 could be repeated for a larger range of current values that will allow a valid conclusion about the relationship made. So remember, we use a variable resistor to vary the current in the circuit. Okay, possible sources of error. Overheating. If you leave it on, you're going to end up with too much resistance. And yeah, we're going to test 3 different components here, aren't we? The bit that people forget on this practical here, guys, is that you must look at number 7, swap the connections going into the power supply. So halfway through, when you've collected values of voltage and current, you're then going to swap it around halfway through and do the reverse so that we can get the positive and the negative side of the graph. Okay, look at this filament lamp here. Okay, very different to the fixed resistor. This fixed resistor follows Ohm's law. And it basically means that as voltage increases, current increases proportionally. Remember, look, this is a line that goes through the origin and it's straight. That means it's directly proportional. Whereas the IV graph for a lamp starts off ohmic, but then the current starts to drop. And the reason for that is because it's starting to get hot and the resistance is increasing. And so the current is starting to drop. And then look, we've got that diode again. They might focus in on the diode. What does a diode do? It only lets current travel in one direction. And the direction of that diode, in fact, I'm going to do that now because it's a good reminder. Okay, just to remind you about diodes. If I have a circuit like this and a diode in the circuit, hang on. The diode will only let the current travel in one direction. So if I have a lamp like this, and this is the negative because it's smaller, this is the positive because it's bigger, and it means that in terms of conventional current, remember conventional current is not actually the way that the electrons move, okay, but conventional current just bear with me, someone's at the door. Okay, and so remember that if the diode is pointing in the same direction as conventional current, then the light bulb will come on and the current will flow. So if I turned that diode round, for example, and redid it, and the arrow was pointing that way, okay, then no, the lamp wouldn't come on. So remember, a diode only lets current in one direction. Okay, so our diode graph ends up looking like this, doesn't it? It's got no current, no current, no current, but then when you reverse the polarity and it overcomes the threshold voltage of 0.6 volts, overcomes the resistance in the circuit, and then we start to get current flowing then, don't we? But remember, this is the negative side of the graph, this is the positive side. This is when it's traveling in one direction, no current at all, and then we flip the direction here, and then the current starts to flow. Remember, you've got 3 IV graphs though, haven't you? That's the one for a diode. You've also got, hang on, it won't move. There we go. We've also got a fixed, excuse me, we've got a lamp. So this is the one for a lamp. Okay, this is current and voltage. Do not, if you were asked to draw this graph, by the way, if you are given half the graph like this, like that, current and voltage, and it asks you to draw the other side in, you've got to pick very specific points and replicate them on the other side. Okay, absolutely replicate them. So you've then got to draw your line in. Okay, now this will curve because this one's for a lamp, isn't it? So it's not a straight line. Do not let it flick up at the end like that. Okay, it should just lay flat at the end if it needs to. So then we've got the one for a lamp, and then we've got a fixed resistor, and the fixed resistor looks like this. It's ohmic, isn't it? And our fixed resistor component is this one, current and voltage. And remember, the gradient on this is I over V. I over V doesn't actually give me anything. Instead, V over I actually gives me the resistance, doesn't it? So my gradient, which is here, is actually giving me 1 over the resistance. Okay. All right, is there anything else I want to go through? Not for practical. So I've looked through a few practicals in the first paper, but now it's down to you to go into this PowerPoint that I'm going to post for you and make sure you look at the rest. Do some of these questions. Yeah, see, we've got the density one there. You've done that a lot, the density one. There's lots to learn from this one as well. Look at all these sources of error which you've got here. Make sure you have a read through these when I post it. And like I said, this one is for the combined. So there's one extra practical, and that's the thermal insulation one, where you're basically, it's very, very simple practical on looking at how the effectiveness of insulators. But yeah, like I said, very, very simple one. All right, guys. So that's it now for paper one. I don't think there's anything else I want to mention. We just have one last look through. No, what I will say, guys, is make sure you know your conversions. This paper is going to be absolutely full of conversions, centimeters squared to meters squared, or centimeters cubed to meters cubed. Make sure you know how to do those. Anything else? No. Okay. Right. Don't forget to come in for all the booster sessions, etc. And best of luck, everyone.